Variables are fundamental in programming. They act as labels pointing to data stored in memory. Think of them like sticky notes. You wouldn't say the sticky note the information, would you? You use it to mark and easily refer to something else. In Python, variables work similarly. They don't contain the data itself. Instead, they hold references like addresses to where the data lives in your computer's memory. This concept is crucial for understanding how Python manages data. Let's dive deeper into how this reference system functions in the next section. Imagine your computer's memory as a vast warehouse with many storage units. Each unit has a unique address. When you create a variable and assign it a value, Python finds an available storage unit in this warehouse and stores the value there. The variable you created then acts as a reference to that specific storage unit's address. So, when you access the variable in your code, Python uses the reference to fetch the actual data from its memory location. This understanding is key to grasping mutability. Mutable data types can be modified directly at their memory address, while immutable ones require creating a new value and updating the variable's reference. We'll explore mutability in more detail in the following section. Mutability in Python refers to whether a data type's value can be altered after creation. This concept is fundamental to understanding how Python manages memory and handles data. When we talk about mutability, we are essentially discussing the ability of an object to change its state or contents after it has been created. This characteristic can significantly impact the performance and behavior of your programs. Think of it like this. A mutable object is like a refillable water bottle. You can change the contents without getting a new bottle. This analogy helps to visualize how mutable objects work. You can refill the bottle with different liquids just as you can modify the contents of a mutable object without altering its identity. This flexibility is one of the reasons why mutable objects are so useful in programming. An immutable object is like a sealed juice box. Once consumed, you need a new one for a different flavor. This means that once an immutable object is created, its state cannot be changed. If you need a different value, you have to create a new object. This characteristic can be both a limitation and a benefit, depending on the context in which you are working. In Python, lists and dictionaries are examples of mutable data types. These data structures allow you to store collections of items and modify them as needed. For instance, you can add, remove, or change elements in a list or dictionary without creating a new object. This makes them highly versatile and efficient for many programming tasks. You can modify their contents without changing their identity. This means that the memory address of the object remains the same, even though its contents have changed. This property is particularly useful when you need to manage large data sets or perform frequent updates to your data. On the other hand, numbers, strings, and tuples are immutable. Once these objects are created, their state cannot be altered. If you need a different value, you must create a new object. This immutability can help prevent accidental changes to data, making your code more predictable and easier to debug. Any modification creates a new object in memory, and the variable's reference is updated. This means that when you change the value of an immutable object, Python creates a new object with the new value and updates the variable to point to this new object. This process ensures that the original object remains unchanged, preserving data integrity. Understanding mutability is crucial for writing efficient and bug-free code. Knowing whether an object is mutable or immutable can help you make better decisions about how to manage and manipulate your data. It can also help you avoid common pitfalls, such as unintended side effects or memory leaks. It affects how data is copied, passed to functions, and modified. For example, when you pass a mutable object to a function, any changes made to the object within the function will affect the original object. In contrast, passing an immutable object to a function ensures that the original object remains unchanged, as any modifications will result in a new object being created. Let's move on to explore various data types and their unique behaviors in the next section. By understanding the differences between mutable and immutable objects, you can write more efficient, reliable, and maintainable code. So stay tuned as we delve deeper into the fascinating world of Python data types. Python offers a rich set of built-in data types, each designed for specific tasks. These data types are the building blocks of any Python program, and understanding them is crucial for writing efficient and effective code. Whether you're dealing with numbers, text, or more complex data structures, Python has a data type that fits your needs. These include numbers, which represent numerical values. Numbers in Python can be integers, which are whole numbers without a decimal point, floats, which are numbers with a decimal point, and complex numbers, which are used in advanced mathematical computations. Each of these numerical types has its own set of operations and uses, making them versatile for different kinds of calculations. Strings are another fundamental data type in Python. They are sequences of characters used to represent text. Strings can be manipulated in various ways, such as concatenation, slicing, and formatting, making them incredibly powerful for handling textual data. Whether you're processing user input or generating dynamic content, strings are indispensable. Lists are ordered collections of items and are one of the most versatile data types in Python. They are mutable, meaning you can change their content without changing their identity. Lists can store items of different data types, making them perfect for a wide range of applications, from simple to-do lists to complex data structures. Tuples are similar to lists, but with one key difference: they are immutable. Once a tuple is created, its content cannot be changed. This immutability makes tuples ideal for storing data that should not be altered, ensuring data integrity. They are often used for fixed collections of items, such as coordinates or configuration settings. Dictionaries are collections of key-value pairs, providing efficient lookup and data retrieval. Each key in a dictionary is unique and maps to a value, making dictionaries perfect for storing and accessing data quickly. They are widely used in applications that require fast data retrieval, such as databases and caching systems. Booleans represent truth values, either true or false, and are fundamental for logical operations. They are used in conditions and loops to control the flow of a program. Understanding how to use Booleans effectively can help you write more efficient and readable code. Understanding the properties and limitations of each data type is essential for writing effective Python code. Each data type has its own set of methods and operations, and knowing when and how to use them can make a significant difference in your programming. We'll delve into how Python handles these types dynamically in the next section. Python's dynamic typing system allows for flexibility and ease of use, but it also requires a good understanding of the underlying data types to avoid common pitfalls and write robust code. Section 5. The magic of duck typing. Python embraces a concept called duck typing. This means Python focuses on what an object can do, not what it is. Remember the saying, if it walks like a duck and quacks like a duck, then it must be a duck. In essence, Python doesn't require you to explicitly declare a variable's data type. If an object can perform the actions required by your code, Python is happy. This makes Python flexible and allows for more dynamic interactions between objects. This flexibility is further enhanced by dynamic typing, which we'll explore in the next section. Section 6. Type hints, guiding Python's decisions. While Python's dynamic typing offers flexibility, it can sometimes lead to ambiguity. This ambiguity can make it challenging to understand what type of data a function is expecting or returning, especially in large code bases or when working in teams. Imagine diving into a project with thousands of lines of code and trying to figure out what each variable represents. It can be a daunting task. Type hints were introduced in Python 3.5 to address this. This was a significant milestone in Python's evolution, aimed at making the language more robust and easier to work with, especially for larger projects. By providing a way to explicitly state what type of data is expected, type hints help reduce the guesswork. Type hints are a form of metadata that provides information about the expected data type of a variable. This metadata acts as a guide for anyone reading the code, making it clear what kind of data should be passed to functions, or what type of data should be expected as a return value. They act as annotations, making your code more readable and less prone to type-related errors. When you annotate your code with type hints, you're essentially adding a layer of documentation that can be incredibly helpful for anyone who might work on the code in the future, including your future self. Think of type hints as adding labels to your storage boxes in the memory warehouse. Just as labels on boxes help you quickly identify what's inside, type hints help you and others quickly understand what type of data a variable holds. This can be especially useful when debugging or extending the code. These labels don't change how Python runs your code, but they help you and other programmers understand the intended data flow. This means that while the type hints are there for clarity, they don't impose any runtime overhead. Python will still execute the code in its usual dynamic manner. Although not mandatory, type hints are a valuable tool for writing clearer, more maintainable Python code. They serve as a form of internal documentation that can make your code base more understandable and easier to navigate. This is particularly beneficial in collaborative environments where multiple developers are working on the same project. Let's move on to some illustrative code examples to solidify our understanding of these concepts. By seeing type hints in action, you'll get a better grasp of how they can be applied in real-world scenarios, making your Python code more robust and easier to maintain. Section 7. Code examples. Seeing is believing. Let's look at some code examples to illustrate the concepts we've covered. Example 1. Mutability Python. My underscore list equals sign 1 2 3. My underscore list dot append 4. Print my list hash output 1 2 3 4. Hash strings are immutable. My underscore string equals sign hello my underscore string plus equals sign world. Print my string hash output hello world. Example 2. Type hints Python def greet name str. Str return hello plus name plus print greet Alice hash output hello Alice. These examples demonstrate mutability differences between lists and strings and how type hints provide clarity to your code. Section 8. Wrapping up. Key takeaways for Python learners. We've journeyed through the fundamental concepts of variables, memory management, and data types in Python. Remember, variables are references, not containers. Understanding mutability is crucial for error-free coding. Python uses duck typing for flexibility. Type hints enhance code readability and maintainability. By grasping these concepts, you'll be better equipped to write efficient, robust, and maintainable Python code. Happy coding!